Has anybody an idea what this flow is? Well, turbulent boundary layer. We have seen already the nice simulation of a turbulent boundary layer of a Philipp Schlatter. This is a simulation of the Aachen group. The flow is in this direction, in x direction. You see essentially the omega isosurfaces of the omega structures color-coded with U. So a lot of these hairpin vortices or half-hairpin vortices and so on. And you want to have a drag mitigation by a traveling wave. So the surface is shaking. We get up to something like 31% drag reduction just with this mechanism. And in our project, we have promised a reduced order model for that. So in the proposal, we have said we want to do a reduced order model like POD. And our reviewer have said, we don't see how it can possibly work, but we give them the benefit of the doubt. These are leading experts. And of course, we knew that this approach would not work. So what could be a good reduced order model for this turbulent boundary layer? So to see the actuation effect. I will show you now a really beautiful brute force model. So what you are doing is that you take your original data. You take your original data, you cluster it. As a number of clusters, you count the number of fingers on your hand. Then you have 10. This is the engineering approximation of infinity. Now you have an infinite number of clusters, and you put your snapshots into the corresponding bins. And so every bin has, for instance, some POD mode amplitudes. We see, for instance, here A1, A2, A3. And so every core switch you see here corresponds to the centroid, the average of the representative state of the clustering. And our dynamical system, we look in our dynamical. So we look in our simulation and we figure out what is the probability going from one centroid to another centroid. You see it here. And what is the average time going from one centroid to the other centroid? And this is our very simple reduced order model of the flow. And we cannot fail because we always stay close to the data. And we have no problems with eddy viscosity or anything like that. This is the purest data-driven approach, which can be fully automated, and you can never leave your domain. And you can also include other actuated states and so on. So, of course, I can now elaborate on the equations which we are using and so on. I would like to focus more on the method of clustering, because this will become more useful to most of you. So now I continue. Why is this close? What about this? Yes. So now I continue. I'm using now slides which Ulrika Kaiser has prepared with an alternative strategy of reduced order modeling. So if you look, for instance, at the mixing layer here, what we do, this is a feature, it's a feature plane of the mixing layer. So you find we are moving around, then we are moving here, moving around, and so on. So in one two-dimensional plane, we now see the dynamics. We don't need to do anything but doing the feature plane and looking at our original data. For instance, if we can immediately see bimodality. So here we will start here, then we could go here, and then we got here. So we get, from this simple proximity map, we can get a pretty good idea of the qualitative dynamics. So what we are doing here, we take the mixing layer snapshots, we cluster it in infinite number of centroids, representative states, and then we build a dynamical system. And let's first do the cluster analysis. If I ask you, what is the number of clusters here in this plane? What would you answer? 3. Yes. So this is obvious to the eye, but now the question is, how do you teach your computer, and how do you arrive at this if you cannot look at your data? So there's one algorithm which is very beautiful, k-means. So what you say, you start with a guess of your number of representative states. I will call them now centroids or clusters. So these are 3 centroids. And of course, it's a very stupid choice. So you say these are the representative states in the next step, you look at the points which are closest to this centroid. So these are the yellow ones. To this one, these are the blue ones. To that one, these are the magenta one. And now you take the average of yellow, average of blue, average of magenta, and you get new centroids. Of course, they look better. And you iterate this until it converges. So at some point, you will have the centroids here, and now these look as reasonable representative states. So this is the k-means algorithm, which I find very beautiful. And what we hope to have solved, we hope to have solved an optimization problem. We want to minimize the average representation error with respect to the data. So if you have a snapshot, and this is the corresponding centroid, then this is the error squared, and we sum up all the errors over all the snapshots. So what we would like now, we would like to determine the centroids in order to minimize this error. So it's a bit like PODs. In POD, you have you also want to minimize the representation error in a statistical average sense.
In this case, you said to the algorithm that you had 3 clusters, right?
Yes.
And so the barycenter would be such that if you tell that you have 4,
yes,
what will happen?
Good question. I would assume you will resolve the other one better. You will resolve the lower one slightly better.
And if you say that you have 10?
Well, then we probably have maybe 6, maybe 5 in the lower one, and then 2 and 3. Mm. Of course, okay. The number of clusters. Now the question is, how do you determine the number of clusters? And there's a sweet spot. The sweet spot is the following. If you say, if I really want to be sure that I determine that my dynamic model, which I build on top of the clusters, is always right, then I say, okay, I take one cluster. Then I know I will always be in cluster 1, cluster 1, cluster 1, cluster 1. So any dynamical model which I make will be infinitely accurate and 100% boring, but the error which I make will be as large as the diameter of my data. Now I can say I'm not smarter. I take as many clusters as I have snapshots. So suddenly I have 2,000 centroids to some extent. I have no compression. And now I have another problem. I know already I go from snapshot 1 to snapshot 2 to snapshot 3. Keyword companion matrix. And at some point, I have to decide what I will do with after the last one. I do not know how I return. So the problem which I have now, the transition matrix, which I would determine now with this maximum number of centroids, would have an extremely large error. So it's only 0 and 1, and we know already if I would have new data, I know already that the transition matrix would have values maybe between somewhere between 0 and 1. So if you do a cross-validation, you get a sweet spot of the error, which you are making with your, say, dynamic model. So not the representation error, but essentially the error in your temporal evolution.
Suppose you have 2,000 snapshots, and as you were saying in your example, you choose, let's say, 1,000 clusters.
Yes.
How does the result will differ with respect to a moving average filter with the kernel of size 2? You're just going to take the mean between snapshot 1 and 2, probably, because the 1 and 2 are the closest one.
Yes.
And then maybe the average between 3 and 4, and 5 and 6.
There's no concept of a moving window here. I mean, this is ergodic. You do not know when the snapshots were taken. So it's like POD. So the order of the snapshots does not matter.
So I guess that the main difference is that while in the moving average you're assuming causality between one and the next, here maybe it can be that the snapshot 5 is very similar to snapshot 900.
There are two things. One thing is a in-sample representation error, which of course increases. Then there's an out-of-sample representation error. So this is the error which you get with cross-validation. For instance, you take 1,000 snapshots to determine the centroids, and then you have another 1,000 snapshot where you determine essentially the error of your representation. Of course, the out-of-sample error must be larger than the in-sample error, but at the end, what you really want to do, you want to have a dynamical model representing your future. So it's essentially the uncertainty of the error which your dynamical model makes in the future. This is a critical thing, and this could be measured, for instance, with an autocorrelation function. I will not go too much in the detail, but there are methods for determining the optimal. There must be a sweet spot. This is clear, and there are methods to determine the sweet spot. Good. So this is it. These are our 3 centroids. Note, centroids, they are the average of the corresponding snapshots. So essentially you can say cluster analysis puts the snapshots into bins. You can also say you have a Voronoi diagram. So you have a decomposition of your state space into different regions. So clustering could mean a centroid, putting things in bin, or having different regions. If you want to do it if you want to use it for other data, for new data, of course, the region is the only relevant, because this can be generalized to new data. Good. So now we go to the mixing layer. These are the feature points of the centroids. You see the one centroid here. These are the snapshots in the corresponding clusters. There are some which are very close to the centroids and some which are reasonably far, but essentially they represent similar states. Then you can look at the transition. So we have a stroboscopic view. We go always a fixed time step further. So when we need to identify something like a transition matrix. The transition matrix tells us the probability if you are on stage in cluster 1, what is the probability to go to 2, 3, and so on. And I will show you how to do this. This is a simple counting. Let's assume we have the clusters 1, 2, and 3, and these are our data points, and we have time resolved our data points. So what is the probability to go from cluster 1 to 2? So 1, 2. Well, you take the number of points here, so 1, 2, 3, 4, 5, 6, and 3 of them go in this direction, so your probability is 3, 6, right? Very, very sophisticated. And what is the probability to stay in the cluster? Okay, there are 2 who do not move, so this is 1. What is the probability to go from 3 from 1 to 3? It's this. So very simple. This is our transition matrix model. We can plot now the probabilities. Our time step has been small, so with a large probability we stay in the first cluster, so, and second, and so on. But say we start with the second, there's a large probability that we go to the third. In the third, there's a large probability to go to the fourth. In the fourth, we go back, so it's second. So here's a limit cycle. And here's also a limit cycle. And how can we leave these 2 limit cycles? Well, if we are here, we can go to with some probability to cluster 1 again, and then we are here. If we are here, we can go with some probability to cluster 1 again, and then we are here. If you are on 1, we can go back to the large limit cycle or to the small limit cycle. So we see a structure in our data, which we may have missed otherwise. We find the same also for the Ahmed body. So 2 oscillatory cluster groups. This is what we call flipper cluster, because this decides if you go right or left. If you have seen the Lorentz system, once you go to the intersection of the 2 ears, you can also go right and left. And if you want to do control and you like this limit cycle, you have to look when you are getting close to your to your 8 centroids, because you don't want to go from here to 1 to here, because you would like to stay here. So you have to find a control strategy which avoids this transition. So it guides you also in your transition. So this is the corresponding dynamics. There are 2 modes, 3 centroids which represent high frequency Kelvin-Helmholtz structures, 6 which represent vortex pairing, 1 which is a flipper cluster. Here are the corresponding modes. You see high frequency states which are convecting in that direction. So essentially you have a phase average here, and you have a phase average here with larger scale energy, and you have the flipper cluster somewhere in the middle. So you now know which game the data is doing. So this is our cluster-based reduced order modeling, distilling this the corresponding dynamics. And I could have added several other things where we got some interesting insights which we would have missed otherwise. So I know I'm a bit over time, but I inquired advance permission. That's why I've answered already a number of your questions. And to summarize, so what did we learn? We learned that reduced order models can be very useful for multiple purposes. Proximity map is a very cool strategy which you should, with which you should visualize all your data. Suddenly outlier detection, dynamics detection, and so on becomes so easy with it, and you can mold it in many forms. For instance, if you have a simulation, an LES simulation and experimental data, an experimental evolution, so you have two trajectories, two attractors, how would you compare those? So if you look in our literature, so clustering allows you to have a pretty objective comparison of two different attractors in terms of their overlap and their corresponding dynamics. So I've elaborated the POD Galerkin method and have introduced one of our codes. I've shown a couple of examples. Our most complex POD model was for the Ahmed body weight, where we needed something like 100 modes to resolve very low frequency dynamics and very high frequency dynamics. And under some conditions, manifold models may be good. I would say when you have oscillatory flow, or when you have flutter, or when you have few frequencies, then you can expect that the data lies on manifold. And this type of model gives you essentially a kind of an optimal autoencoder. And under experimental conditions, you can apply something like our feature-based manifold model. And if you want to fully automate your modeling procedure, you may want to consider clustering. Clustering is really so brute force data oriented. You cannot do anything wrong, and you will learn a lot. And at the end, you can always build a reduced order model, a subspace model based on your clustering. And with this, I want to conclude my lecture.
So questions? Yeah, I have like 100 more or less. But
I like the response, everybody raising the question.
Maybe I will ask you mine at the coffee break.
Yes, in the examples you gave, your number of modes was always 2. What happens when you have 20 or 100? I mean, how do you do K-clustering then, and how do you interpret K-clustering then?
Very nice question. You would always like to interpret your clusters, but there's no guarantee that you can. So what you are effectively doing with a clustering, you are looking at something like short-term averaged or something like ensemble averaged coherent structures in a certain neighborhood.
Time information.
Well, I mean, it's time and things that may be happening in different places in the flow field. I mean, assume that you are trying to see thunderstorms in the Midwest.
Yes.
There's one here, there's one there, that happen at different places.
Well, good point. So what you do with the clustering, you assume that you cannot afford to have sparse data. You have to be full data. So if you need to have one centroid for the cluster for the thunderstorm here, and one centroid for a cluster at another location. So if you have anything which is distributed, you suddenly need a lot of centroids. And you have the same problem also with a POD. If you have just a moving vortex, you may need of the order of 100 POD modes just to describe a single moving vortex, and clustering comes with the same disadvantage. So here you would rather like to use some Lagrangian structures or something.
Just worried because you said that this cannot fail, and I can see cases in which it can fail.
It can fail. And what you are typically assuming, you're assuming that you have something like an ergodic situation, in the sense you have your data, and somehow your data points are visited again after some period of time. When I looked originally at the data, for instance, of Wolfgang Schröder or LES data. So initially, in the proximity map, the data looked a bit like a worm. So you go from here to here to here to here. So now you cannot identify any model, any dynamical model, because after a half circle, you may go in this direction, you may go back, you may decide to stop. So everything is now left to your fantasy. So what you need to have, you need to have essentially enough data so that you can go back or to your original data. So the data points need to be something like recurrence points.
But that's not ergodic. Ergodic means that you go through all the points in the phase space. Your dense, your
yes,
trajectories. You're saying a cycle. You're speaking about a cycle.
You're reasonably dense in your state space, and you can't be too dense, because then you are losing on your prediction again.
But then you're thinking of something like a cycle, which is a single structure.
Well, it works for the turbulent boundary layers. So for all the turbulent boundary layers which we have, we can, after sufficient amount of data, we can build something like the cluster-based reduced order models, and they have this ergodic property.
I mean,
of the transitions between the coherent structures, between the centroids. So
but there are many. I mean, in that picture that you had there, you had, a thousand structures. Yes.
You're referring to that one. Very nice. Well, so what we see, so we average over a significant portion of the domain. So it's something like, I think, over one streak length and the whole spanwise length and one boundary layer thing, a lot of things. So what we are effectively seeing, we see the flow response to the traveling wave. So we do not see the rip vortices and sweeps and
okay, so you're thinking of the wave.
Yes, yes. But in principle, you can add 100 centroids, and then you can see more structures.
But then you cannot see it. I mean, you cannot see 100 things. I cannot see 100 things.
No, but you can process it.
Yes, but I cannot. I mean, what's the point of doing a K cluster then, if I'm going to be lost in these 100 clusters, these 100 centroids?
Well, number one, for instance, you can see what are the high drag states, what are the low drag states, what is the dynamics. I'm going from how do you go to these high drag states. So essentially, you can identify precursors to undesirable events. So there are some events where you have significant drag increase, and you can pinpoint them to a few centroids. And you can see, and you can look at your dynamics, and you see you are entering these undesirable events from this set of.
You're still thinking of a low-dimensional space in which you can see things.
Not necessarily. No, where you can compute things.
How?
Well, let's assume one thing. Let's assume there's one. Let's assume you have one state which is very undesirable, very high drag. Let's assume this. And let's say this state is called is a cluster number one. So what you can do, you can go back. You can say, how do you go to cluster number one? You will go over cluster number, let's say 2, 3, 4, 5, 6. So now essentially you have created the trajectories. You have coarse-grained your trajectories to your undesirable event. And now you can ask yourself, what do I need to do so that I do not go on this trajectory? So this is where your human experience comes in.
My human experience will not help in a high-dimensional space. I know that. I mean, more than 3, I just cannot see things.
No, but you don't need to see things.
Well, then how do you interpret them?
But it's very easy. For instance, if you are if you are interested about drag, you look at the drag of every centroid and you sort them correspondingly.
But, I mean, it's never going to be as easy as that. There will be a high drag region here and a low drag.
Yes. And then you can average, and then you can distill the events. You can do something like conditional sampling,
because
and so
they're going to be jumping around.
For instance, you can do conditional sampling in a very beautiful way. But you always need some auxiliary models on top.
The chairman getting there.
Okay.
We can continue here. We stay here. You can go. Yeah, there is another one, and then probably we go and we continue. We queue for the questions.
very beautiful, and this is the purpose. Essentially, what you can now do, you can look at the transition times through your clusters. You can look at the cost function of the clusters. If you have a cluster, the advantage is you can average over all the snapshots in the clusters, and you get the corresponding coherent structure. So you filter out the noise. So the centroid is essentially a noise filter over your neighborhood. And my view on the cluster-based model is they do a nice job of pre-processing your data, and from there on, everything is based what you actually want with your data. For instance, you may decide to make your POD model in certain regions. So this has been done by Gunzburger. So you decide you want to have some representation of the high drag dynamics, some representation of the low drag dynamics, or maybe you want to figure out where are your quasi attractors. So essentially a group of centroids in which you quickly rotate and where it takes a long time to move out. So this is the social dynamics for which there also exists a beautiful analytics. So now on top of the cluster-based models, you can do many analyses, and these many analyses become very easy after your discretization, because you just need to count your fingers on your hand and the corresponding variables, and without it, it would be next to undoable.
Okay, so there's one last, and then those that want to stay, and the other can go.
My question is about the dynamic part.
Okay.
You mentioned the probability, and I got it, but you mentioned the average time going from one cluster to the other.
Very good, very good. So you caught me already that I was talking about two different models. So there's one model where we essentially have a stroboscopic view, where we say every delta t, we determine the transition probability. Now, the problem with this ansatz is it's a bit too diffusive in time. It's very good for the statistical averages, but it's a bit diffusive in time. If you want to, for instance, model the autocorrelation function more accurately, then it's then we resolve. Then we don't have the stroboscopic view, but we look at the trajectories. And then we characterize, we go from trajectory 1 to 2 in this period of time. So we have a much more accurate representation, and we can also have a linear interpolation between centroid 1 and centroid 2, and then we go from 2 to 3 and so on. And now we go one step further. We say, okay, why do we go from centroid to centroid? We can start anywhere, and now we just use the centroids for local interpolation. And now we go one step further. We say, okay, we do local interpolation between the different centroids. Why don't we add our actuation, our control laws? So there are different control laws with different parameters. You can consider them as being different dynamics and different flaws. And now if you change, you have another actuation parameter, we move between the centroids, between two operating conditions. So now this becomes a very essentially a versatile tool for also including your being able to interpolate your actuation. So we did it for the turbulent boundary layer, and it has very much surprised us. So at the end, what you are saying, you try to be as true to your data as possible. It's not as brute force as k nearest neighbors, where you just look at the nearest neighbors. Essentially, you coarse grain things in bin. But from there on, you do the interpolation between your centroids, coarse graining the snapshots in the corresponding bin. And I would argue if you have 10 centroids, your resolution, if you allow yourself to interpolate between the centroids, your resolution is not much worse than if you take 10 POD modes. But you have one advantage, you will always stay close to your data. You can never go to infinity. Could also be considered a disadvantage, but for model robustness, this is an advantage.
Okay, so I propose we have a 15-minute break and we start again at 4. Is it okay? Thank you. Thanks again to Professor Noack.